very simple now. Okay, I absolutely don't think that you will have any issues. And then some problem, you will find this is very, very simple to understand now. And then one problem with resistance parameters. Actually, I think I forgot something. So, okay, so Thevenin's theorem, don't need to worry. So this is the circuit which we can use, simple circuit. And then so that's the characteristics of the torque speed. So starting torque, and then the full load torque, which is very close to this thing, and then pull out torque. So maximum torque you have, what you can have in the motor. So usually the pull out torque is 2 to 3 times of the rated full load torque. Okay, so that's the depends on the motor, but usually it's like that. So that side is usually the motor, but sometimes you can actually run the motor, induction motor, as induction generator. Okay, so if you want to run the motor as generator, of course then somebody has to run the rotor. Usually you have seen wind power. Wind power, the machine is the induction generator. Okay. So then it reverses the characteristics. So if this side is the induction generator, so you are running. So you need to run the rotor more than the synchronous speed. You have to run the rotor more than the synchronous speed. Then it will run as a generator. So induction generator.
So if you've got a wind turbine and you ran enough current through, you could get it to blow in the air instead.
Can you repeat again?
Yeah. Could you turn all wind power generators into a giant fan? Could you theoretically do that?
I mean, you can say that, but what you are comparing, wind power generator is a generator, because wind is running the fan, but normal fan which you are talking about running by electricity.
Yeah.
So the operation is opposite.
But if you switch the flow of current, could you make it blow air?
Yeah, that's right. So you can switch the current flow. So that means once you switch the current flow, that means the fan, you have to now rotate the fan. So then you just simulate the wind generator. You understand? So the power flow diagram completely reverse. So in the motor, power comes from the electricity. You get the mechanical output. But when you talk about the generator, okay, so this the comparison is similar, but the power flow reverse. Okay, so this part we did not do. The maximum torque occurs when the power transport is maximum, so R2 by S is maximum. So anyway, so this part we did not do. I think that's the maximum power, maximum torque. So that's when you use slip rings. Yeah, so actually you had a question before in the multiple choice. So it does not depend on the resistance, but resistance can decide where the maximum torque can occur. Okay? So if you remember the position of the maximum torque, it can vary if you vary the resistance. But they cannot make the torque change. Torque will remain the same, but the position or the speed at which it occurs, that can be controlled. So that's what. So earlier days, when the drivers like inverters were not available, lot of research was done on induction motor because people want to control the speed. So that was one of the method by introducing resistance in the circuit. And that was not possible in the cage rotor because cage rotor, the winding is short circuited. On the slip ring, you can introduce external resistance. So this was done for the slip ring induction motor. Okay, so there is some problem again. So please go through those problems because I might give the problem which has been solved and available to you.
I have a feeling we'll need a formula sheet.
So do we need the formula?
We've covered so many formulas in the last 3 lectures.
You think that you have got so many formula, but you have got only one circuit.
Yeah, but lots of variables.
That's true.
Lots of variables. And I don't mean like for the synchronous speed, rotor speed, frequency. Those ones are all pretty simple.
Okay,
A
so
lot of the ones we did today are just...
so watch out for an email on Friday night.
Okay. Are we getting an email, sir?
Huh?
Are we getting an email? I'll do it.
We'll see. If I set up the questions and I feel that similar, maybe you will get something that you can bring some effort sheet.
Nice.
So watch out for the email on Friday. Okay. We got the parameters. Now if I ask you, how do you determine those parameters by test? Okay. Motor manufacturer might give you some parameters, but think of that motor manufacturer forgot to give, or motor itself is an old motor, and the task for you is to give me those parameters by test. What can you do? So we'll discuss about those tests, what you need to do. So what are the parameters you need?
Stator coil resistance.
Stator coil resistance. So many times when I draw a circuit, you see a lot of times I'm just changing the things, isn't it? Doesn't matter, I change but I don't change much.
What happened to RR? Okay, I was thinking that was the load. I'm like,
Okay, so how many parameters you have got?
5.
6.
7 if you count voltage.
RS,
I
XS,
don't think I count frequency.
RC, XM, XR dash, RR dash. SIP is not the parameter you need to determine because that is the variable given. So, how do you determine those parameters? Those who have done 362, if you remember, we tried to determine those parameters of a transformer. But unfortunately, we could not do successfully because of some problem in the setup, because the power factor wattmeter was not working properly. Okay. But yes, so we can do that here. So first thing what we do is to determine the stator resistance. How do you determine the stator resistance? How do you measure the stator resistance?
Resisted.
Yeah,
Run a current through it and see what
DC
I mean,
voltage.
yeah, the simplest thing you may say, I can actually take the terminal and measure by ohmmeter. Okay, it's still good, but you are talking about 3-phase. So how many terminals you have got? You have got 3 terminals, isn't it? So it can be like this. So 1,
the fact that it's literally on the board helps.
3, or you can have the situation like that. One, 2, So if I say that yes, you can do using ohmmeter, how do you get that?
Is there a neutral point? Is there a thing that you could stick one of the leads or anything so that is the neutral point?
Neutral point is there, but usually not available to you. Usually is not available. If you remember, one of the group last week, those who did in the morning hub, Jimmy was in the afternoon hub. You opened the motor. So those that group who did not see the open motor, so tomorrow you can see the open motor. So on the top you see that 6 terminals are coming and 3 terminals are short circuited to make the neutral point, but you do not have access because it's closed. Okay? So you do not have the access, but you have access of these 3 terminals. So what can you do to determine the resistance of the winding?
Presume all the windings are the same resistance, so just measure both and then divide by 2.
What if you don't know if it's a star?
Yeah, you stand up, reduce the speed, compared to my speed it's slow, and tell it again so that everybody understands.
Oh, well, you've got 2 terminals. If it's a delta, you connect 1 to 1. If it's a star, you connect 1 to number 1 and number 3 and then divide by 2.
Did you get everybody? So what he told that, okay, forget about delta, star, assume all the windings are exactly equal. That means all the resistance are equal. So you can measure any 2 and divide by 2. So that's what we do. So we measure between 1 2, but we just cannot keep 3, make 3 unhappy. Okay? So we measure between 1 and 2, measure between 2 and 3, measure between 3 and 1, average them, then 1/2 of that value will be the resistance. Do you get me? So it will be R, R, R. So if you measure between 1 and 2, you get 2R. If you measure between 2 and 3, you get 2R. If you measure between 3 and 1, you get 2R. So take the average. Then you get 2R. So you take half of that. So if the winding is star connected, you do this way. If the winding is delta connected, what you do? You do again between this, average. But in this case, R and 2R is parallel. So what will be the equivalent? So equivalent will be R times 2R by 3R, isn't it? So 2/3 R. So you have to take 3 by 2 of the resistance what you measure. Do you get me? So that's by ohmmeter. But actually, the recommended method is not by ohmmeter. Recommended method is called DC test. Have you heard of that?
Yes, it's all about
DC test.
It doesn't come to our-
So what do you mean by DC test? What do you mean by DC test and why do we need to do DC test?
Yeah, for that.
So DC test is required to know the DC resistance. So you cannot use AC because AC means you will also have inductance. So you cannot measure resistance by AC. Do you understand? By alternating current, you cannot measure resistance because you will have inductance placed into your measurement. So that's what you have to give direct current. So you have to apply direct voltage. Now another reason of applying direct current is you need to make a path. You need to make a path of current flow. When current flows through the windings get heated up and you allow the winding to reach a steady state temperature. So you actually measure some kind of warm resistance, not cold resistance. You understand? So that's why DC test is important. So if you do DC test, what exactly you do? You need to supply a voltage, low voltage, and you have to connect a ammeter. You have to also measure the voltage by voltmeter. So you measure the voltage, you measure the current, and you get the resistance by Ohm's law, voltage by current, and that gives you the resistance 2R. Similarly, you can do between these two, you can do between these two, and then R by 2. So the method remains the same, but you are allowing a current to flow, so that the winding they warm up and you actually can measure the warm resistance. Clear? So that's the first test you do. So you got, what did you get? You got RS. So out of 5, out of 6, 1 done. Only 1 done.
Do the same thing for rotor.
Same thing you cannot do for rotor. Unfortunately, rotor doesn't have terminal.
You built in for that purpose exactly.
That is, you can get for the sleeve ring where you have the terminal, not for squirrel cage. Okay? So squirrel cage induction motor, you do not have rotor terminal. So tomorrow you will see. Those who have seen, you should not tell that. You open the motor, man. Did you see the terminal of the rotor?
I would have guessed you just have connected on the tops.
Yeah, but that all circuited. How did you get that?
Yeah, you just get the resistance of the actual armature. You wouldn't get the resistance through the wire, you could get through the steel rod that it's all mounted on.
Yeah. Okay.
Ah.
So what do we do to get the rotor resistance? So for the rotor resistance, we need to do a test called block rotor test. As the name suggests, what do you think the block rotor test? Yes, you hold the motor, so motor doesn't rotate.
Not with your hand.
Or you can do by hand if it's a small motor like half a kilowatt. But usually you need to allow something on the shaft so the motor doesn't rotate. Now if the motor doesn't rotate, what do you expect the current? Current will be too high, isn't it? So you cannot apply rated voltage. So you give very small voltage, okay? You give very small voltage. How much? Around 10%. Around 10% of the rated voltage. If you apply only 10% of the rated voltage, what do you think about the flux? What do you think about the flux? At the 10% of the flux, isn't it? So flux will be very small. So if the flux is very small, then what do you think this part? This part disappears, isn't it? Because this is very small. Pole loss will be very small. Flux also will be very small. So this part disappears.
With the block rotor test, if we don't know the air gap, the best we can do is a guess for the rotor resistance?
No. Air gap is there because you are applying alternating voltage, not the DC voltage here.
Yeah, but if we don't know, like we could have very low resistance armature, but a slightly bigger air gap,
Yeah, but
we don't know how much is taken up by what.
yeah, so it does because you will get approximate value.
Yeah.
Okay, you get approximate value. So usually you get alternating voltage 10% because of the low value of the voltage. This part, and what happened to the S?
If it's not rotating, it's 0.
0?
No,
One.
1.
Sorry.
So it's 1. Okay. So now you measure current. So you measure voltage, current, and power. You measure voltage, current, and power. Okay. So you are applying alternating voltage, which is very low, 10%, and then you measure. You don't allow the rotor to rotate. You hold the rotor, and then you measure the voltage, current, and power. So what is the power here now? So power here now is this, isn't it? So you know RS already. You already RS because of the DC test. So you can find out R. Clear?
Do the impedances not affect it that much?
Yeah. So impedance you get, okay, so then get XS plus XR dash, because impedance Z is what? Z is actually so RS plus R dash you already got from the power equations, so you can get XS and XR. So now what you do, you just take approximate there 50%. Some company says that 60-40, some company says 50-50, like that. So usually 50-50. Okay? So you take half of each. Okay? So you got 4 parameters: XS, XR, RS, RR dash. So next one is remaining as what?
Running test.
Running test. So you have to do the no load test. Everybody follow this one? Long rotor test. We get the series parameters.
Did the core losses, like core copper loss and impedance, not affect this?
Yeah, because of the voltage is very low.
Right.
So because of that flux is very low.
Yeah.
Okay, so flux is very low. That's why core loss there will be there, but it will
very,
be
very small.
very small. Because you cannot say that I get 100% accurate. You cannot, because you are ignoring something.
Yeah, because I was just thinking, if we're only doing 10% of the rated voltage, if it's a very, very high voltage motor, it's still a fairly large
Yes.
resistance and impedance we're ignoring.
So there will be some.
So it's a percent accuracy,
Yeah.
not.
So you will
Yeah.
have, but at the end of the day, you think that what exactly you are going to get. You are going to get the approximate circuit parameters, which will be useful to analyze your induction motor.
Yeah.
So that's like you can say, oh, this will be like that. But if you want to do the real thing, you have to do the real test.
Yeah.
Okay. But real test sometimes is not possible. Like for example, those who are working with NASA, they cannot every time make a satellite to send, so they have to do a lot of simulation.
Yeah.
But at the end, simulation does not give them 100% thing. They have to send some satellite, and some satellite will go to the sea, some satellite will go somewhere else. Finally, few satellites will go to the Mars, isn't it? Or whatever it is. Okay? If you believe that Mars rover exists. I don't believe so. Okay, so now we have the last parameter. So that's called no load test or running test.
Yeah, right.
So in the no load test, effectively the motor is allowed to run without any load. So what we can do here, we can think of that because the motor is running at no load, ideally what do you think the slip?
0.
Slip will be close to 0. Okay? If slip is close to 0, this part will be very high. If this part is very high, what do you think this current?
Low.
This current, there is no current. So you measure the voltage, so you get the voltage, current and power. So you measure voltage, current and power. From that, you determine these two. But you can understand this is the approximate circuit. Our actual circuit was these two was here, isn't it?
Yes.
So there will be some influence of these two on those parameters. So ideally, if you want, what you can do, you can take here and then this voltage, instead of this voltage, what you can say, the voltage across this is E. So E will be V minus I RS plus JXS.
That's ideally, but
Yeah. So that's the current which is flowing, and you can actually take away what is the drop across these two. But still, if you ignore, still you can get pretty good result. So you can get all these 6 parameters. Okay?
It's still acceptable.
It's still acceptable because in actual characteristics you will see that these two did not play any role.
Yeah.
Okay? So this just gives you the core loss. So you get the core loss very accurate. So that's the test. Sorry. So DC test, no load test, and block load test. So we have those. And what I was talking to Jamie, that how do you actually divide? So the manufacturer tell you what type of motor and how do you divide. So design A 50-50, design B 60-40, 30-70, 50-50. Okay, so these are the, so you need to know what type of design and then you can divide. But
question, what's that one? Live motor? What?
no, this actually inductance. Okay, this inductance which you have determined. XLR is the total inductance. Okay, and how you are getting for both. So 50-50 is pretty good without much error. So then example on that. Yeah. So a lot of things we have covered. No, so we're not so end yet. So I will just quickly tell you something here. Before the inverter came, not inverter, even now, have you seen who has got fan in his house or apartment? Fan. Okay. So what type of fan controller you have? Is it a big one or small one? Small one. If you have big one, that's basically a big resistance. And the resistance gives you terminal, so it actually increase the resistance value when you decrease the speed. But if you have a small one, they use a device called triac. Have you heard of the device?
Yes,
Yeah.
because you made us read the 468 report.
What?
Only those of us who chose that report.
I didn't choose that one.
So you have you heard of thyristor?
Yeah.
So thyristor is basically, so you have heard diode, isn't it?
Yes.
So what the diode does for you?
Current flow
One direction.
So diode allows the current to flow in one direction, isn't it?
with a voltage threshold.
Yeah, of course you have to apply voltage. You need to make anode as positive with respect to cathode. So for example, if I have a diode, so this is my anode, this is my cathode. Diode will be like a gatekeeper. So if you go with a ticket to watch either a rugby match or maybe some kind of concert, there are gatekeepers. They will allow to enter if you have a valid ticket. At the time of entrance, they don't allow anybody to go out, isn't it? For exit, there is different rule. So diode is like that. They will allow the current to flow only in one direction. Okay? So if you say that my anode is, depending on the material, is 0.7 volt higher, so anode voltage VA should be greater than VK plus 0.7 volt for it doesn't matter what type of circuit you have got. Anode must be higher than the cathode by 0.7 volt for a silicon diode. So diode will conduct. But if I have a device, it doesn't matter what is the anode voltage with respect to cathode, unless I control it by another voltage with respect to this G to K. Then it becomes control diode. Okay?
So you change to 0.7.
It will be 0.7 you required, but also you actually need to give a voltage of the G, which is called gate, with respect to the cathode. But the direction of the current, it remains the same, anode to cathode. So current will always flow like that.
So it's a bit like a one-directional transistor.
Is one directional diode, but one directional controller. So if you use this type of device, you can actually control DC, isn't it? DC. You cannot control alternating current, because alternating current means you need to allow the current to flow in both the directions. So what usually does, you have to have another diode, another thyristor, anti-parallel. Okay? So that's called thyristor. Okay? So in 1960s, they were very, very popular. Even today, in Australia, I do not know, but like in New Zealand has got two islands, North Island, South Island. South Island is famous for power generation, electricity generation. North Island is famous for consumption. Between North Island and South Island, there is the Cook Strait. Okay? Under that Cook Strait, which is almost like 1,700 kilometers, they have that high voltage DC transmission. Thyristor is famous for high voltage DC transmission. So that voltage is 765 kilovolt. Okay? And 1200 megawatt of power it can transmit. So DC transmission. You understand? So thyristors are famous for high voltage DC transmission. So actually they have got different applications, not for normal use. But if you think of that, we need to control the current flow in both directions. You can make like this. Okay? So of course instead of 2 gate, you can make 1 gate. So then it becomes triac. So what you see here is basically triac, is basically a triac. So what it does, it allows the voltage or the power to flow under your control. So instead of starting from 0, you can start from any place. Okay? And you can control the voltage and then corresponding power. So basically when this fan, you want to change the speed. So what you want is to give low power. So you can make the power, this is called firing angle. So where you actually fire. Okay? So this firing angle or starting angle, you can make close to 180 degree. So if you give 0 degree, you are allowing whole cycle to pass. So that maximum power you are giving. But if you make 180 degree, you allow 0 power. So you can control the power input, and the power input is related to torque.
So is it the same for car AC as well?
I think in many applications it is, but now because of inverter, an inverter is cheap, so they don't go for this. One of the problem, have you seen, those who have got little this thing, make the speed very small and try to listen whether any sound is coming. If you have not heard, do it. Okay? Still it's now winter, but still you can do it for a few minutes. Just see the noise. What actually happens when you run this at like 90 degree or something, you are not allowing the whole cycle, it generates a lot of harmonics. And that harmonics produces that sound. So it's not that sound. It's not that sound, not the massive sound of the sometimes those who are sensitive, they cannot actually sleep with that type of sound, because that sound is very, very irritating. So this is one of the biggest disadvantages of that. Even harmonics is a big topic, but it can produce a lot of harmonics.
What are they using to control the track in this case? Because it has a different
what they
Probably a threshold.
what they do, how do they control the,
Yeah, what's controlling that? I mean,
The gate, yeah, what's,
the period, the function of the triad.
so basically the function actually it should be, so what actually happened,
what is the gatekeeper?
no, so I mean you want to know the physics behind it.
Well, because you said, so here you've got a sinusoid is offset by some phase. And I'm wondering what generates that function. How you generate that function?
How you generate that function? So you have to give some voltage here.
Yeah.
So once you start the voltage, give the voltage, then the triac will start. So you may say actually how it happened. So
Resistance.
no, it's not resistance. So it's basically a semiconductor device.
Right.
So semiconductor device, you know diode, PN, and then you come to transistor. Either you go for PNP or you go for NPN. Okay, but then thyristors is actually called PN. So in case of transistors, you have got like this, isn't it? Collector, base, emitter. So so here what happened? You have got holes and you have got electrons. So depending on whether you reverse bias or forward bias, your electrons and hole will play a role. So when you forward bias, then of course the electrons carrier will go there and then continue the current flow. When you come to transistors, it actually starts between base and emitter. When base emitter forward biased, then your current flow like that, and then the circuit starts with this. Now, when you have got transistor here, okay, this actually you can do two transistor analogy. So it can come like this. So you have got 3 and okay, so like this. So oh no, sorry, this one. Like this. Okay. So this is, let us say, anode, cathode, gate. So anode, cathode, and gate. So under normal conditions, if you do not have this, then it does not actually conduct, because this both actually this is switched off and this one also not getting any current. So when you give some current, it starts conducting. Then when it conducts, because you are hitting the base, it starts conduct. So it's called PNPN device. Okay. So effectively, you are controlling the flow of current by giving a gate signal.
In this circuit here, where's the gate signal coming from? Is it just a voltage threshold?
Is the voltage. So you do not need to give a constant voltage. You can give a pulse.
Yeah.
So because once it starts,
but that pulse would come from the AC, and it's just it has a threshold.
it's
So once it gets through that, it'll open the gate.
Yeah.
Yeah.
So you have to design a separate circuit for that.
Yeah.
To give that DC voltage. Once it starts, it will continue conduct. One of the problem is you actually cannot switch it off once it starts.
What?
So for AC applications, it goes, when it goes to 0, it switch off. That's called natural commutation. But in DC, you cannot switch it off. And you have to make separate circuit to bring the current, forcing the current to 0. That is one of the biggest problem. Okay? But for AC, alternating current is okay. If it goes to 0, it naturally switch off. So anyway, so we are going too much. So, so effectively, you can control the power. So I think we might take a little bit. So that was one of the way of doing the speed control of induction motor in the early days. Okay, using triac to control the voltage, but doesn't do well. Okay, so I think I'll stop there. Okay, so next week.